I think. So, welcome. Pierluigi Vallarino is from Aarhus University, and the title of his presentation is Time-Varying Kernel Densities as Dynamic Infinite Mixture Models. So, the floor is yours, Pierluigi.
Thank you very much, Alessandra. So today I'm presenting this paper where we introduce a family of semi-parametric models to track the time-varying distribution of a time series. And we do it by exploring an analogy between kernel density estimation and mixture models. Now, before proceeding, just a quick note, this is a single authored paper, but it owes a lot to Alessandra's and Leopoldo Catania's supervision, and I'm very thankful to them. So why we do it? First of all, well, lately there's been a growing interest in modeling the time-varying probability distribution of a time series, called this process Y. For instance, like we just seen with Francesco, tracking the time-varying distribution of GDP growth allows policymakers to understand the evolution of relevant quantities, such as macroeconomic uncertainty and macroeconomic tail risk, by which I mean the risk of a sudden contraction in economic activity. Now, usually in this literature, the focus is on the so-called predictive distribution of the process. That is the probability law of the time series at a point in time, say little t plus 1, given an information set, f, at time little t. And f usually contains all past information on y and eventually on some explanatory variables. What's our proposal? Well, we suggest to approximate the predictive density function that is the one of interest with an approach inspired by kernel density estimation. However, kernel density estimation was devised to study the so-called unconditional distribution of the process, that is the probability law of the time series, the very same point in time as before, t plus 1, but given no conditioning information set. And this is, of course, not our case, in that we do have some conditioning information, which furthermore entertains a temporal dimension, as it is given by all past information of interest. So we must find a way to include this past information into kernel density estimation. Now, early attempts at this task are due to Harvin Doroshenko as well as Jeon and Taylor, but unfortunately, as you're going to see in a couple of slides, they don't work so well in practice. Wang and co-authors as well as Garcia and co-authors tried to improve upon these early approaches by devising new ways of estimating the very same modeling strategy. So same modeling approach, different M estimators. What we do? Well, we tackle the modeling strategy itself and do it by proposing a flexible family of semi-parametric models that are based on kernel densities. And I say flexible because model components can be adjusted so as to capture certain characteristics of the data. Estimation of members of this family relies on a maximum likelihood approach. We study the asymptotic properties of this maximum likelihood estimator under a misspecified context. And in practice, we find that this family performs well when it comes to tracking and predicting the time-varying distribution of US GDP growth. So now to the modeling part. This is the DIM family, dynamic infinite mixture models. We're going to understand why in a couple of slides. The starting point is a stationary ergodic sequence, YT. It is univariate, real-valued, and we take it to be square integrable. It lives on this probability space. We keep it with a filtration that at point t, at time t, considers all past information on the process. So insofar, there won't be any explanatory variable. Like I said, we suggest to approximate the density function of interest with this functional form that you can read here. Basically, it is an infinite weighted average of kernel densities, calligraphic K, each of them centered around the past value of y, yt minus I. They all share the same scale or equivalently bandwidth component, so that the smoothness of the approximating function form will change over time, because this bandwidth is time varying. Like I said, this is an infinite mixture, so we have some weights. The omegas, they're positive, summing to 1, and we take them to be a decreasing function of I. In this way, more importance will be attached to kernel densities centered around more recent values of the process. And this seems to be reasonable in a time series context. Now, I believe that most of you are familiar with traditional kernel density estimation, so here let's trace a sort of a timeline. The starting point is standard kernel density estimation. We are in a stationary ergodic setting, so the unconditional density function will be constant over time. And here it is approximated by this weighted average. There is again a bandwidth component that is usually taken to be a functional form of the sample size, capital T, for instance, proportional to some power. Harvey and Dorishenko, as well as John and Taylor, started from this approach and extended it to the predictive density function. What they did? Well, they considered these weights here, theta between 0, 1 to the power of I times 1 minus theta. So we have an exponentially fast decay with respect to I. Then we have this static bandwidth parameter h. The smoothness of the functional form will now be constant over time. What we do? Well, we extend this approach, we generalize it by letting the bandwidth vary over time and by considering other weighting schemes, so basically new ways of incorporating past information. Essentially, this is an infinite mixture of densities based on dynamic components, and that is why this family of models is called DIM, Dynamic Infinite Mixture Models. So the first point is the choice of the weighting scheme. We can start from exponentially decaying weights, what's that in the literature, and then we move on to hyperbolically decaying weights. We have a power law decay with respect to I. There is a parameter theta to be estimated from the data, larger than 1 for convergence purposes. We then move one step forward and introduce an additional parameter lambda strictly positive, so as to improve the flexibility of hyperbolic weights. Again, lambda will have to be estimated from the data jointly with theta. For the bandwidth, we pursue a so-called observation-driven approach, whereby at time little t, we know the bandwidth for time little t plus 1. In particular, h t plus 1 is given by a static function form phi of itself at time t, and of an innovation term epsilon t that we assume to be this one step ahead predictive error. This is the error you make at time little t minus 1 when predicting y at time t. And indeed, mu hat is the one step ahead predictive mean based on this family of models. We're going to see an expression in the next slide. Now, h acts as a sort of, let's say, scale component. So we can borrow something from the literature on time-varying scales in order to construct this function phi. And in particular, we start by a Garcher-like recursion, where we have the squared bandwidth, an innovation term, as well as an autoregressive component. Then we consider a GGR-like recursion, where we introduce a leverage part in the stochastic recurrence equation. And in this way, negatively and positively signed predictive errors will have a different impact on the bandwidth. Finally, we move on to the DCSE-Garch recursion. This is inspired by the literature on robust filtering, on score-driven filtering in particular. And here, the log bandwidth h tilde again follows a four-component recurrence equation. We have an innovation, an autoregressive part, and again a leverage term. Now, the innovation is based on ut. So ut is the new driving force. Ut is a function of the square predictive error with a range between -1 and nu. Nu is larger than q and to be estimated from the data. So ut is a random variable of bounded support. The driving force will have a bounded support, and in turn, the bandwidth will have a bounded support. We're going to see afterwards what are the empirical consequences. Just a quick word on the predictive moments. Thanks to this infinite mixture representation, we can derive closed-form expressions for the k-step ahead predictive moments of any order, and at any forecast horizon k larger than 0. Here we have expressions for the one-step ahead mean and variance. Both moments are taken under the probability measure p hat. P hat is the probability measure based on approximating model that we are proposing, and needs not to coincide with P, the true probability measure that characterizes the sample space, therefore the data generating process. We are leaving that P unmodeled. We're just proposing an approximating misspecified model. For the one step ahead mean, we have this infinite weighted average, while for the variance, we have these two components additive structure. The second component, this positive difference you can read here, dictates the long-term behavior of the variance process. Short-term adjustments are driven by the squared bandwidth, the squared predictive bandwidth, which is the first component. So of course, this is a family of models. There are some parameters. We gather them into the vector of parameters theta. Like I said, this is a mean-specified family of models, and that is why we carry out inference with minimizing the Kalb-Calabre divergence between the true probability measure, as implied by the unmodeled true density function F0, and the model-based probability measure, as implied here by our approximating functional form F. So in practice, we start from a sample, y0 to capital T, finite length, from the process of interest, and use it to obtain a sequence of filtered, or if you prefer, empirical densities, that then is employed to define the maximum likely estimator of theta star. It is theta hat. It maximizes this log likelihood function you can read here, where little m observations are discarded so as to initialize the kernel estimation procedure. We derive conditions such that theta hat is strongly consistent with respect to theta star, and also asymptotic and normally distributed. Like I said, mean-specified model, so sigma will possess the usual sandwich form, with the filling of the sandwich having a peculiar structure due to the mean-specification, dynamic mean-specification of the model. And if you're interested, these conditions and structure are in the appendix to the slides. Now, just a quick overview of
how strong are, Pierluigi, these conditions? I mean, the conditions that you need to get consistency and asymptotic normality.
I would say that conditions for consistency are rather mild. We give general conditions for the entire family of models and then show that they are satisfied for each specification we are proposing. So weights and bandwidth we saw before. They are a bit stricter for asymptotic normality. That is pretty much almost always the case, but I would say they're not excessively restrictive. We don't require, for instance, Gaussianity or sub-Gaussianity of the process of interest. We just have some moment conditions. Does it satisfy your question?
Yeah.
Would you like to see the conditions?
No, please go ahead. I mean,
all right.
We got 6 minutes.
All right, so just a quick overview of the results. We look at quarter-on-quarter growth rate of US real GDP and consider 12 instances of this family of models that are obtained by combining the weighting schemes we saw before with the free bandwidth processes plus a fixed bandwidth. So that when we have exponentially decaying weights and a fixed bandwidth, we are back to the case of Harvey Doroshenko and Jean and Taylor. So what's there in the literature? As a starting point, we estimate a model with a fixed bandwidth and compare the estimated weights, which you can see here, plotted as a function of I, so of the lags. Now, under EWMA weights, omega 0, so the weight attached to the most recent information, is much smaller than under hyperbolically decaying weights. So much more importance will be assigned to more recent information under hyperbolically decaying weights than under exponentially decaying ones. So we conjecture that a model based on EWMA weights will be less responsive to new information on the process. And we visualize this conjecture by plotting the predictive mean over the subsample that you can read here under the 3 weighting schemes. The black solid line is the EWMA-based predictive mean. It is much smoother than the hyperbolically based predictive mean, and this is due to the fact that shocks take much more time to reabsorb under these EWMA weights than under hyperbolically decaying ones. This is a consequence of what we saw before. We then compare what happens with different bandwidth processes, and to this extent, we look at the predictive standard deviation over the very same subsample as before. We now have a green line. This is the data of the most positive predictive error, and a red line, the data of the most negative predictive error. In black, we have fixed bandwidth, so what's there in the literature. And we see that this is a very smooth process, showing that we can't have a timely incorporation of new information on the process into the variance using this fixed bandwidth. On the other hand, we see much more temporal variation when we have dynamic bandwidth, the other 3 lines. It is nice to see that with the gauge bandwidth, we have spikes both after the positive and after the negative predictive error. This is a byproduct of not having a leverage term. The leverage term is there under the GJR and the DCS e-gauge specifications, And indeed, now we see spikes, relative spikes only after the very negative predictive error. As a consequence of a boundary innovation term, the DCS variance spikes much less than the GJR1, and we see it here right after the Great Recession. The purple line spikes less than the light blue one. Just to conclude, we have some diagnosis checks on the residuals. So we look at standardized one-step ahead predictive errors and plot the sample autocorrelation functions, both in the levels and in the squares. Hopefully, we would like to see no serial correlation. So here we have the sample ACF for standardized predictive errors. We see some autocorrelation for EWMA weights, while it disappears under hyperbolically decaying weights. So EWMA weights do not provide a very good fit to the predictive mean. As to what concerns the squared predictive errors, we don't see much serial autocorrelation with dynamic bandwidth, while there is autocorrelation with a fixed bandwidth. So a fixed bandwidth may not be ideal in capturing the conditional heteroscedasticity of the data. So we introduced a family of models that approximate the predictive distribution of a time series of interest, and in doing it, we are generalizing and apparently improving upon excellent approaches to kernel density estimation for time series data. We propose a maximum likelihood estimator, study large sample properties, conduct finite sample analysis in the paper, and show that we can reliably track the time-varying distribution of GDP growth. In the paper, we also have model diagnostics based on probability interval transforms, a forecasting analysis, and some finite sample analysis. But that would have been a bit too much for the time being.
We're done. Thank you, Dan, Pierluigi. So we have time for a question. If
Can I ask you a question, maybe?
Yes, please. Sorry?
Can I have?
Yeah, sure. Go ahead.
Okay. Yeah, thanks, Pierluigi. Really interesting application of also your model, and the general framework seems to be really new, at least I think. Can you go back where you describe, for example, the evolution of the bandwidth and the time varying moments also, maybe? Yeah, because I was wondering here, because you defined then, so the updating. Can you hear me? Yes. Yeah. This is the right one, the right slide. Because you defined then the residual that you are using for updating these basically Garch equations for let's say observation driven through this prediction error. But then if I have well understood your model strategy, you retrieve this residual based on infinite past, because mu_t then depends on the infinite number of observations, right?
Yeah.
So these Garch equations, basically, even if they have this kind of Markov structure, because it depends only on the previous step, actually they are not. So I was wondering, related also to the question that Alessandra did before, about your assumption, especially on the consistency, because usually, for example, in Garch or also score-driven, we require some Markov condition. So, for example, the stochastic recurrence equation, in your case, in the classic one, will never work because you have the infinite fast. So I was wondering if you have something related maybe to the stochastic recurrence equation with infinite memory of Wittenberger and authors like that, or if you have something else, I don't know. So I was wondering about again the assumption that you should have for obtain consistency, especially.
Okay, I got your point. It is completely right. Epsilon t has to be in a certain sense initialized, because in practice you won't be able to observe all the infinite, right? You will truncate your predictive mean to the first point in the sample. What you do in the paper is we let's say show that this initialized, if we want, predictive error converges at a certain rate, at a certain desired rate, to this, let me call it unfeasible infinite path predictive error. And on this convergence of the predictive error, we base our convergence that the bandwidth you initialize, the one you find in practice, converges again at a desired rate towards this, and now we agree, unfeasible bandwidth, because this bandwidth requires to go back into the infinite past. In practice, you can't do it. We have to show that the initialized converges to the, let's say, infinite one, the feasible. We'll show it by showing exactly what you said, the convergence of the initialized predictive error sequence towards the infinite memory, let's call it this way, predictive error sequence.
No, I get it, but the question wasn't okay. Maybe I don't have time.
No, I'm sorry. I mean, no, we don't have.
All right, sorry.
Time now. We can, postpone this nice discussion after. During the break, right? So
Yeah,
we have
sure.
a further
Thanks,
talk. No. Thank you for raising it, and thank you for for the discussion. But I suggest that we postpone it. During the break in 20 minutes after the next talk. So let me thank Pierluigi for the nice talk, and I stop the recording now.